Good. Well, welcome back to our third lecture here today. I'd like to remind you before we go any further that what we are doing here is, again, just skimming across the cloud top, so to speak, and looking at various aspects of the fundamental ideas associated with hypersonic aerodynamics. And we're not going in any depth, and we're certainly trying to avoid a lot of quantitative expressions. We're just doing a lot of qualitative work, trying to show a little bit here and a little bit there. If you feel like it's a lot of material, you're quite correct. It is really a lot of material. If you feel like maybe you're being blown out of the water, don't worry about it, because I have a feeling a lot of people get blown out of the water by this sort of thing. What I suggest is you sit back and relax a little bit and just sort of let it seep in and continue, especially again for those of you who do not have the book material in front of you. Just do the best you can, watching the screen, listening to what we're talking about, giving a little bit of thought. And once again, I'll recommend that you then obtain the material at a later date so that you can fill in some of the gaps, and you can kind of remind yourself about what it is that we've been talking about. We're going to pick up where we left off at the end of our last discussion. Let's go back to our roadmap once again, please, to see where we are. We're still talking about inviscid hypersonic flows. We are down here talking about basically exact methods, the method of characteristics. I want to say something very quickly about the blunt body problem, which is an example of what we call finite difference solutions. It's an example of computational fluid dynamics. The solution of the flow over a blunt nose body, say like this pen again with a blunt nose, was a major research problem in the 1950s and the 1960s. Finally, it was a major research problem. Literally millions of dollars and tons of talent and tons of time was spent to try to solve for that flow field, particularly the flow field in the vicinity of the blunt nose, called the supersonic blunt body problem. In 1966, there was a breakthrough in that problem, utilizing what we call a time-marching solution. And the idea is this. If we go back to our Euler equations, our original Euler equations, and just write them so that the time derivatives are all isolated on the left-hand side, so that effectively we have spatial derivatives on the right-hand side, then I think you can see how one might set up a computational technique where you would calculate the flow field around a given body in steps of time. And after a large number of time steps, using these time derivatives, calculate the flow field in steps of time. And after a large number of time steps, if you had a steady free stream and you had a steady body, then this unsteady flow would asymptotically approach a steady state. The steady state is the answer that you're interested in, and you've used this time-marching approach only as a means to that end, obtaining that steady state solution. This seems like an awfully hard way to solve a steady flow field problem, but I guarantee you that it makes the blunt body flow field problem infinitely easier to solve. The reasons for that are basically mathematical. I don't want to go into that, but other than to say that if you look at the steady flow over a blunt nose body, and I'll hold this pen up again, if you look at the steady flow over the blunt nose here and behind the shock wave, you have local regions of subsonic flow and local regions of supersonic flow. And the Euler equations in the subsonic region have a mathematical behavior called, associated with what are called elliptic partial differential equations. And you go downstream to the supersonic region and the mathematical behavior changes to hyperbolic behavior. The equations are all the same, it's just their mathematical behavior changes. And this causes a major problem in the solution of that flow field. Whereas if you go and look at these equations, if you have the time derivatives in these equations, the whole system becomes hyperbolic with respect to time, no matter whether your flow is locally subsonic or supersonic. So this allows a well-posed problem to be obtained, solving the blunt body flow by means of a time-marching technique. Let's take a look at what that means and some results. Figure 520 on page 181 gives you the shock wave shape over a blunt nose body. What we're looking at here is Mach 4 flow over this blunt nose body, and we're looking at the mechanics of this time-marching method. In other words, we start out at time zero, some initial condition with an assumed shock wave shape and an assumed flow field between the shock and the body. And then we start this time marching procedure using the unsteady Euler equations, calculating the time derivatives of velocity and density, and advancing the flow field in steps of time. You can see that after 100 time steps, the shock wave has moved out here. After 200 time steps, it's out here, but it's beginning to slow down. After 300 time steps, it's here, and it's pretty stationary. 400 and 500 time steps later, it hasn't changed anymore. That's the steady state. To look at this further, let's look at the pressure at the stagnation point. Here is a plot of the pressure at the stagnation point as a function of time. The stagnation pressure, function of time. Starting out at time 0, at early times it ranges all over the map, and then it kind of comes in here and homes in asymptotically to the proper steady state. Again, this is the answer we're interested in. All these transients are just a means to that end. For the graduate students, my graduate students who carry out these types of time marching solutions, I always tell them, you get a great big fat batch of output, you tear off the last page, you keep that, and you throw everything else out, because it's that last page that you're interested in these time marching solutions. If we just look qualitatively at what some of these blunt body solutions look like, at least the flow fields, let me show you this. Here are some final steady state shock wave shapes and sonic line shapes for Mach 4 flow and Mach 8 flow over this parabolically shaped cylinder. At Mach 4, the shock wave is out here, and the sonic line for Mach 4 is this line right here. As you increase the Mach number, what happens? The shock wave moves in closer to the body, and the sonic line moves down closer to the center line. These are typical characteristic variations in a supersonic and hypersonic blunt body flow field. Shock wave moves closer to the body as the Mach number increases. Shock wave moves closer to the body, and the sonic line moves closer down to the center line. Now, for those of you who ever have dealt or will deal with blunt body, supersonic and hypersonic flow field solutions today, you will be dealing in one form or another with these time-marching computational approaches. Now, here is an ultimate in such a blunt body type calculation. I'm just going to show you some results. Here are some calculations, time-marching calculations that were made over a shuttle-like shape at high angle of attack. So a large portion of the bottom surface of the body was subsonic flow. We're looking at a computational grid up here wrapped around the body in the longitudinal plane and also around the azimuth of the body, around the body. There were close to 100,000 grid points in this calculation carried out at NASA Langley. This was done a number of years ago. A time-marching solution of the Euler equations. This gives you the three-dimensional shock wave shape around the body. These little flutes here are just a quirk of the graphics filling in between mesh points. But this is an example of a relatively modern three-dimensional time-marching inviscid hypersonic flow field calculation. This is kind of an example of what you can do with these things. If we look at the pressure distribution as a function of distance along the center line of the space shuttle from these calculations, you get this kind of variation. Again, it's just an example of how well the computational results given by these curves, the solid curve here, compares with the actual flight test data from the space shuttle. These are actual flight test pressure measurements from the space shuttle. So computational fluid dynamics, when we start talking about exact solutions in hypersonic flows, we're talking about computational fluid dynamics. We're talking about solving, when we say exact solutions, that's a misnomer. Time out for a minute, a little philosophy. Exact solutions. That means that you're solving the exact equations for the physical model that you're dealing with. We're dealing with an inviscid flow. The Euler equations are the exact equations for that physical model. When we go through a numerical solution, don't fool yourself. You're not getting an exact solution of those exact equations. You have numerical errors, round-off error, truncation error, and so forth. But whenever I use the word exact solution, the word exact is in quotation marks, it means that we are at least attempting a numerical solution with the equations in an exact form, that all the relevant physics are in the terms in the equations. Okay, Yes, question.
What is the gamma E?
Oh, good question. Let's go back to figure 529. The gamma sub E, gamma 1, first of all, 1.4 is the ratio of specific heats for standard air. The gamma sub E is an attempt to try to fudge high temperature flow effects by using an effective gamma, gamma sub E, gamma effective of 1.2. Good question to ask. In fact, I'll elaborate on that a little bit later on today when we're talking about high temperature effects. Now, let's go on further and look at some other detailed flow field calculations, exact solutions. Another one, a three-dimensional flow field calculation, was carried out, and one of the very first ones carried out in the early 1970s. A three-dimensional hypersonic solution of the Euler equations was carried out over this sort of a little bit of kind of like a shuttle-like body by Paul Cutler and his colleagues at NASA Ames. Using that kind of configuration, certain results are obtained. For example, shock wave shapes. This is a plot of in a planform view and in a side view of the calculated and measured shock wave shapes over this body. Calculated shock wave shapes, three-dimensional time marching. Sorry, this is a spatially marching Euler solution, and very reasonable agreement between the calculated shock waves and the measured shock waves. It's just simply saying that the computational fluid dynamic solutions for three-dimensional flows and hypersonic flows used solving the Euler equations are pretty well in hand. I'm going to show you one last result and then we'll leave this. This is a plot of pressure coefficient as a function of distance along the bottom surface of the space shuttle. Very similar type calculations we've just been looking at, solving the Euler equations by computational fluid dynamics, finite difference solutions. What we see here is a result for Mach 23. The shuttle is at, the shuttle is at 30 degrees. Up here we have a 30-degree angle of attack. We have the open circles are Mach 8, and these are calculated CFD results for Mach 8. The solid circles are the calculated CFD results for Mach 23. And what do you see between Mach 8 and Mach 23? What you see is virtually no difference at all. What you're looking at there is the principle of Mach number independence alive and well, where the pressure distribution between Mach 8 and Mach 23 in terms of the pressure coefficient now is essentially the same. Here's a similar set of calculations for a 20-degree angle of attack, and you can see the same Mach number independence. So again, I'm using this figure for double duty. First, to show you again more additional, we'll say additional computational fluid dynamic results for hypersonic flows, exact solutions of the Euler equations, and a second duty to drive home the idea of Mach number independence. Okay, now with that, we are going to move on to another portion of our roadmap. What we've just done is basically wrap up our discussion of hypersonic inviscid flows. Let me remind you again that we've just been going across sort of bumping across the cloud tops. The idea here is to try to give you a little bit of a flavor, a little bit of feeling, physically, principally a physical feeling of what's happening in hypersonic inviscid flows. Now, we're going to go to the second part of our roadmap, namely a discussion of hypersonic viscous flows. Hypersonic viscous flows. And let's first look at a few basic aspects of these hypersonic viscous flows. So once again, in your notes, for those of you who have the book, that is, we're now starting part 2, which begins on page 211. Viscous hypersonic flows. To begin this discussion, we're going to concentrate on chapter 6. We'll be talking about some boundary layer results and make a few comments about aerodynamic heat. So for the next few minutes, this is what we're going to be dealing with. I'm going to start this discussion off a little bit by looking at a velocity altitude map in figure 6.3, and this is a velocity altitude map, just as we looked at with a slide demonstration earlier today. Well, let me remind you again that a flight path of an entry vehicle on a velocity altitude map starts out at high velocities and high altitudes, and as the vehicle penetrates the atmosphere, slows down following a path like this. This is a typical, this band in here is a typical flight path for a lifting entry vehicle like the space shuttle. And superimposed on this velocity altitude map are lines of constant Reynolds number per meter. And the purpose of this is to show you that for a substantial range of flight during the entry of these hypersonic vehicles, we encounter reasonably low Reynolds numbers. And these reasonably low Reynolds numbers mean large swaths of laminar flow, and they also mean fairly strong viscous effects when you have low Reynolds numbers. So this is a motivation for talking about viscous hypersonic flows. Okay? Now, earlier we looked at the governing equations for inviscid flows. They were the Euler equations. Now, on page 217, let's look at the governing equations for viscous flow. These are called the Navier-Stokes equations. Again, you know, now you see them, now you don't. I just want to show you that they're there, they do exist. The continuity equation, the x, y, and z momentum equations, and now we have shear stress terms in to account for the viscous effects. The energy equation, which now has terms involving thermal conduction as well as shear stress and normal stresses, so that we're dealing here with a now totally viscous flow. The Navier-Stokes equations are the exact governing equations for a viscous flow. Now, the solution of those equations is not easy. And let's go to our roadmap for a minute. We're going to sidestep the solution of these equations for a few minutes, the same way that people did historically. In the 1930s and 40s and 50s, people looked at those Navier-Stokes equations, and even going back as far as the 1904, people looked at those Navier-Stokes equations and they said, my gosh, they're too hard, we can't solve them. So let's simplify them. And in 1904, Ludwig Prandtl introduced the boundary layer concept, which was, in my mind, worthy of a Nobel Prize, but he never got one. But in any event, he came up with the basic idea of splitting off the viscous flow field over an aerodynamic body as being a boundary layer constituting a boundary layer adjacent to the surface where all the viscous effects are contained, with an inviscid flow outside the boundary layer. Now, this is not news to most of you, but this is a way of sidestepping the Navier-Stokes equations, because if you look at those Navier-Stokes equations and you put in the physics of the boundary layer, namely that the boundary layer is assumed to be thin and the Reynolds number is reasonably high, and if you put in the physics of the boundary layer into those Navier-Stokes equations, you will get something called the boundary layer equations, and you can find these on page 226. We're going to look at them for a minute. These are the equations that govern, and really, let me draw a quick picture here before we go any further. If we have an aerodynamic surface, like a flat plate, aerodynamicists always love to draw flat plates. And we're saying that adjacent to the surface, there is this viscous boundary layer with a certain thickness delta, in which all the viscous effects are contained. And the equations that govern the flow here inside the boundary layer are these boundary layer equations. They're much simpler because they must have much fewer terms, and they have a mathematical behavior that's parabolic, which is much simpler than the original Navier-Stokes equations. So we're looking at the continuity, x momentum, y momentum, and energy equations in the boundary layer. Now, these equations can be applied to hypersonic boundary layers. There's something I'd like to toss out to you, however. For those of you who are familiar with boundary layer solutions and feel comfortable with these boundary layer equations, let's go back to the overhead for a minute. I want to point out to you that the y momentum equation says the partial p respect to y equals 0. Let's draw a picture here. Here's the y direction. And it is part and parcel of the boundary layer assumption that comes through in the y momentum equation, that the pressure does not, and the pressure in going normally through the boundary layer, the pressure does not change. The partial p respect to y is equal to 0. That's a normal assumption of zeroth order boundary layer theory. Now, and that comes about because of, and I'm going to show you on the previous page, that comes about from an order of magnitude evaluation of the Y momentum equation. Now, this gives you no details, but in the Y momentum equation, looking at the orders of magnitude of the terms in the Y momentum equation, that's what these are, orders of magnitude. On the left-hand side, you have terms of order of magnitude delta, which is very small because the boundary layer thickness is assumed to be very small. So these are really dinky small terms. Same over here. And that means that the pressure gradient ought to be a dinky small term so that the orders of magnitudes of the left and right-hand sides of the equation balance. That's what this equation is saying. And that's why you always end up by saying that that the partial of P respect to Y equals 0 in a boundary layer because it's very small, so let's put it equal to 0. Since we're discussing hypersonic aerodynamics, I just want to point out something to you. If we go back and look at this order of magnitude reduction, there's a Mach number in the denominator. And if the Mach number becomes large enough, this can become a dinky small term just on the strength of that Mach number becoming large. And this is telling you that inside that boundary layer, the partial of P respect to Y does not necessarily have to be nearly 0. And there is a statement here. I'm going to read it to you in the middle of the page. For very large hypersonic Mach numbers, the assumption that pressure is constant in the normal direction through a boundary layer is not always valid. And this is something interesting to take into account, or keep in mind, put it that way. That what this is saying, this says that, look, the pressure gradient through the boundary layer can be 0. And we make hypersonic boundary layer calculations all the time, making that assumption. But what this is also saying is that if you go into a wind tunnel and you measure a viscous flow over a hypersonic body, and you go through the boundary layer, and you measure a meaningful pressure change, maybe a 10 or 20% pressure change through the boundary layer in your hypersonic flow, don't take your data and throw it up and say something's wrong, because it could very well be right. Because what we're saying here is that in that hypersonic boundary layer, because you have that high Mach number, the boundary layer equations show you that you could support a pressure gradient in the Y direction. So it's just something, it's a physical thing in a way to kind of keep in mind. Now, however, people go on and carry out boundary layer calculations in hypersonic flow all the time, making the assumption, namely this assumption here. We'll wait for the overhead camera to come up. The partial P respect to Y equals 0, and you get good results. So once again, we're not destroying this result. We're just simply saying, look, in a hypersonic boundary layer, you may have a little bit of extra flexibility here, and you may actually have situations where there is a non-zero pressure gradient, and if you see it, don't worry about it, because it could be, it's justified in being there. Now, we'll come back to referring to that a little bit later on. Let's take a look at solutions of these boundary layer equations, just to begin to get a better physical feel for essentially viscous boundary layer solutions. What does some of these solutions look like? Let's visualize hypersonic flow over a flat plate. This is figure 6.6, page 243. Hypersonic flow over a flat plate. What we have plotted here are velocity profiles through the boundary layer basically as a function of Y. Visualize, let me draw a picture here. We'll go back to this picture. Let's imagine that we are looking at a given XY's location. So there's the X coordinate right there. And let's look at the variation of velocity through the boundary layer as we go in the Y direction through the boundary layer itself. And that's what this is right here. Here's our Y direction at a fixed X and a fixed Reynolds number. And here's the velocity U divided by the velocity at the outer edge of the boundary layer. Notice that it's 0 right at the wall. And notice that, by the way, there are a number of curves here, one for each for a different Mach number. If we pick a Mach number like Mach 8, notice the velocity starts out at 0 at the surface. It increases up to the external velocity, UE, in other words, it goes to, this ratio goes to 1 at this location, at this Y location. So what we're looking at are velocity profiles for a number of different values of the free stream Mach number at a given location on a flat plate. Now, for a given Reynolds number, look at what's happening as you increase the Mach number. As you increase the Mach number, as you go from 4 to 8 to 12 to 16 to 20, this is the outer edge, the end of these curves are the outer edge of the boundary layer. Witness that the boundary layer is getting progressively thicker and thicker as the Mach number increases. Conclusion, in a compressible high-speed flow, as you increase the Mach number, everything else being equal, the boundary layer thickness increases. As a matter of fact, you can show that for a laminar boundary layer, the boundary layer thickness grows as the square of the Mach number. And you can see that happening. Look how rapidly that thickness is growing as we're going up in Mach number. So that's one physical characteristic that you can get out of boundary layer solutions. And by the way, these are boundary layer solutions for what we call an insulated plate, an insulated wall. There is no heat transfer to the plate. The wall temperature is such that there's no heat transfer to the plate. We can get temperature gradients through the boundary layer. Here's our temperature profiles. Same scenario. This is temperature divided by temperature of the edge as a function of distance y through the boundary layer. Temperature varies like this. Notice what happens as we increase the temperature, as we increase the Mach number. As we start out, essentially, as we start out low Mach numbers, we're dealing with fairly low temperatures, in a sense. The temperature T over TE ratios may be like 10. But as we go to higher Mach numbers, we're going to very large temperatures. Conclusion, at high Mach numbers, you have high temperatures inside your boundary layer. So again, the solutions of the boundary layer equations are clearly showing you that you can have high temperatures within these boundary layers, and that's a very important fact. Okay, again, we're just simply showing effects of hypersonic viscous flows. If we have a cold wall, if we have a hypersonic flow, say, over a cold body, here are some velocity distributions for a cold wall flat plate. And let's compare these with the velocity distributions we were just looking at a minute ago for a hot wall. Okay. Now, let's pick a Mach number. Let's pick Mach 8. At Mach 8, for the hot wall case, we see the velocity profile increases, so we get to 1 out here. This is the edge of the boundary layer at Mach 8. It shows this is the Y location, the edge of the boundary layer. It's just slightly less than 20. Here's Mach 8. Here's the edge of the boundary layer out here. The only difference is that we have a cold wall. Not a hot wall, not an insulated wall, but the wall is cold. Look at the boundary layer thickness. It's a factor of 10 smaller. It's 10 here instead of 20 here. Conclusion. When you have a cold wall, everything else being equal, the boundary layer thicknesses are smaller. Why do you think that is? On a physical basis, why do you think that would be the case? Pardon? The density again, of course. The density. Why the density? Because if we look at the temperature distribution for this cold wall, here is a plot of our temperature profile as a function of distance y through the boundary layer. Starts out here at a low temperature near the wall, increases to a peak temperature inside the boundary layer, then decreases back to the outer edge temperature. Let's compare these temperatures with what we would have with a hot wall. So I have to fold this a little bit differently. We will now look at these side by side. Here is our adiabatic wall case, temperature profiles. Here's our cold wall case, temperature profiles. Witness, at Mach 20, we're talking about temperature ratios that may get no higher than about 16. But for the adiabatic wall case, the temperature ratios are up to 70. Conclusion, when you have a cold wall, you have you at least have cooler temperatures in the boundary layer. And like we talked about earlier this morning, if the temperature is cooler in the boundary layer, the density is higher. If the density is higher, the boundary layers get thinner. And that is why, everything else being equal, when you have a cold wall, the boundary layer is thinner. So again, just some of these physical variations, things that we are talking about for hypersonic flows. Next physical question. What is the effect of Mach number on skin friction? Well, the answer is given here in figure 610. This is a plot of skin friction coefficient as a function of Mach number on a flat plate. What do we see? For a given wall to free stream temperature ratio, pick any one of these curves, we see that the skin friction coefficient decreases. Physical conclusion, the effect of Mach number on skin friction coefficient, now not the shear stress itself, but the skin friction coefficient, the effect of increasing the Mach number decreases the skin friction coefficient. Same thing happens with heat transfer. Here's a variation of heat transfer as a function of Mach number. The heat transfer coefficient decreases as the Mach number increases. This is a Stanton number, by the way. I really apologize for having to go so fast on these things, because normally if we had a lot more time we'd talk and pause on these things. I'm going to pause here. For those of you who don't know what a Stanton number is, it's defined as the heat transfer to the surface divided by the velocity, the density at the edge, the velocity at the edge, times the adiabatic wall enthalpy minus the wall enthalpy. So it's a heat transfer coefficient, and that frequently in aerodynamics you'll see the Stanton number used as a heat transfer coefficient for aerodynamic heating. Sorry, oh yeah, I'm sorry, we'll leave it there for a minute. This is also defined in your book. Somewhere in there you'll find the definition of the Stanton number. Okay, now let's go on to, let's look at some more boundary layer solutions here. These are solutions, all these solutions we are looking at for a flat plate. Let's now turn the tables. Let's go back to looking at this kind of body. And let's look at the blunt nose on this body. In particular, let's look right at the stagnation point on a blunt nose body. The solution of these same boundary layer equations, I'll put them back up here. The solution of these boundary layer equations, when carried out for a stagnation point instead of a flat plate, a stagnation point leads, and the way it leads is given in your book, but we're just going to look at the results. The results are given here. If we have, first of all, a cylinder case, and by the way, by this I mean a circular cylinder. Let's take the pen. Let's go back to the pen. Orient it perpendicular to the flow. Flow is going in this direction. Pen is perpendicular to the flow. And we're looking at flow over a circular cylinder. And we're looking at the stagnation region of that point. On the overhead camera here on the screen, you will see an equation that is a result of boundary layer theory that gives you the heat transfer to that stagnation point. And what does that heat transfer depend on? It is critically dependent on something called the square root of dUE dx. Let me tell you what that is. We'll draw another picture here. Here is our blunt nose body. Here's our stagnation point. We'll let x be measured in that direction. UE is the velocity tangent to the body, external to the boundary layer. dUE dx is therefore the gradient of velocity at the stagnation point. So when you say dUE dx is the gradient of the velocity at the stagnation point, that gradient of velocity at the stagnation point critically determines the heat transfer to the stagnation point through this expression. If we, instead of having a cylinder, if we just had a sphere, like an axisymmetric body, we get this equation for the stagnation point heat transfer. Again, please visualize this as just a solution of our boundary layer equations. If you've never seen this solution before, these equations look like black magic to you, but don't worry about it. These are results. Just simply accept these as results for stagnation point heating values that you can use in a hypersonic flow on a blunt nose body. Now, I want you visualize this equation in your mind with this coefficient point 763. I'm going to flip back to the cylinder result. The equation is identically the same except the coefficient is a little bit smaller. This says that the heat transfer to the cylinder, everything else being equal to the stagnation point of the cylinder, is smaller than the stagnation point heat transfer to a sphere. Here we have 0.57 for the cylinder. Here we have, for the sphere, 0.763. Question, does that make sense? Why is that? Does anybody know why that would be the case? Why would the heat transfer to the sphere at the stagnation point be higher than the heat transfer to the stagnation point of a cylinder? Here, if we come back to me for a minute, imagine my fist is a sphere. Why would the stagnation point there, why would the heat transfer to the stagnation point be higher on that sphere than it would be if my arm now is a cylinder perpendicular to the flow, and the heat transfer along the stagnation line here is going to be less? Why is that? Well, geometry. Yeah, geometry. Yeah, exactly. It's something in aerodynamics that we call the three-dimensional relieving effect. Think about this for a minute. Look, if we have a two-dimensional body, this pen here is a two-dimensional body. Go this way. Imagine this flow going over this pen. This pen sticks out towards you to infinity and back over my shoulder to infinity. And you're the flow, and you're flowing over this pen. And you come up here and you say, man, I've got to get out of the way of this pen. Well, you only have two choices. You can either go up and around it or down and around it. Just two choices. That puts a certain constraint on you. You get kind of uptight, right? A little constraint. Okay. Now, let's turn this pen around. Okay. Now, here's like a, let's use this. This has a spherical nose. It's hard to see, a spherical nose. So the pen now is aligned with the flow. It's a three-dimensional flow. Now, here you are, the flow. And you're coming along here, and you got to get out of the way of the body. Well, you have an option. You can go up and over, you can go down and around, but you can also go around and to the side. That's an extra degree of freedom. Therefore, you're less tense about this. You're more relieved about it. And in aerodynamics, this is called a three-dimensional relieving effect. And what this does for you, among other things, in the three-dimensional case, the three-dimensional relieving effect makes the boundary layer thinner. And if the boundary layer is thinner in the at the nose region, what does that mean? If the boundary layer is thinner, how does that affect your heat transfer? Here's a nose, flow coming down in this direction. Here's a thin boundary layer. Okay? Here's a nose, flow coming down in this direction. Here's a thick boundary layer. So the boundary layer thickness is that thick. It's thin over there. Now, at this point, we have, let's say we have stagnation temperature. It's a high temperature. At this point, we have the wall temperature. The change in temperature is just simply T0 minus T wall. But what affects the heat transfer? Heat transfer, some of you may recall, is the thermal conductivity times the temperature gradient at the wall. Okay? Out here, we have T0. Out here, at the wall, we have TW. We have a delta T, which is still the same, T0 minus TW. But for this thin boundary layer, what do we see? The temperature change across the boundary layer per unit distance, a delta T over the boundary layer thickness. This thing is a lot higher for this picture than it would be for here. If we take this and divide it by this thick delta, we're going to get a smaller ratio. What this says is, for the thin boundary layer, the temperature gradient at the wall is a lot larger than the temperature gradient at the wall for the thick boundary layer. And this is why, for the sphere, this is the case for the sphere, this is why the heat transfer to the sphere stagnation point is higher than the heat transfer to the cylinder stagnation line. Okay, so all of this comes out of boundary layer theory. Now, back to our equation for the stagnation point heating, just for a few moments. Emphasize again, in this equation is the square root of this velocity gradient at the stagnation point. The velocity gradient at the stagnation point, in turn, can be obtained by assuming Newtonian flow and using some of the geometry as the following expression. You can find this on page 256. We find that the velocity gradient varies inversely as r. r is the nose radius. Draw a picture here again. Here's our stagnation, here's our flow, Here's our blunt nose body, here's our stagnation point, and the radius of the nose is r. And what we see here is that the velocity gradient varies inversely as r. And if the heat transfer, as we see here, varies as the square root of the velocity gradient, that tells us that the heat transfer is inversely proportional to the square root of the nose radius. And here is the classic result that we all, virtually that is well known, and I'll just read it here. Stagnation point heating varies inversely with the square root of the nose radius. Therefore, to reduce the heating, you go with a large nose radius. Now, let's go back to our slideshow for a minute, earlier this morning. Remember that X1 I showed you and the F104 I showed you? We said, man, they had sharp noses and sharp leading edges. That's because heat transfer at Mach 2 is not very important. Heat transfer at Mach 1 is less important yet. But visualize the space shuttle that flies at Mach 25 and think of that big fat nose on it, large nose radius. That's why the nose radius is large, because when you start flying at Mach 25, heat transfer becomes very important. And so you start designing your vehicle to try to minimize the heat transfer. And that's why you have blunt leading edges and blunt noses on hypersonic vehicles. And it is a result of boundary layer theory as applied to hypersonic, applied to, say, the stagnation point case for a compressible flow. Okay, now if you don't believe that result is a theoretical result, here is a plot of experimental data. This is our, we'll wait for this to come up here. This is Stanton number as a function of Reynolds number based on the nose radius, so you can just visualize this as increasing nose radius. And the experimental data all fall along a band like this. This is a log plot, and the slope of this line is -1/2. And so as it shows that the heat transfer varies as the square root of the nose radius on an experimental basis. Okay, one last thing on this, by the way, since we're talking about aerodynamic heating. We talked about stagnation point heating. Let me point out to you, if you might ask the question, how does the aerodynamic heating in a hypersonic flow around a blunt nose body vary as you move away from the stagnation point? As we, let's say, phi be our angle measured away from the stagnation point. Well, here's the result. This is heat transfer measured at any particular angular location divided by the stagnation point value. Here, 0 theta is the stagnation point, so that's why we have 1. These are experimental measurements of heat transfer as you move away from the stagnation point. You can see that heat transfer drops like a rock, as you would kind of expect it as you expand around the body. So this is a typical variation. It's kind of like a cosine to the 3/2 type of variation around the body. Now, question. Stagnation point heating looks pretty high. Question. Would you think that the stagnation point on a hypersonic body is always the point of maximum heat transfer, therefore? What do you think? This will always be the point of maximum heat transfer. Well, the answer to that is not always, because if we go back to this curve, this applies to a laminar flow around this body. If you would do something, or if something would happen to trigger transition on the forward face of this body, you would end up with a turbulent flow that might have a local heat transfer. We've kind of recognized that aerodynamic heating in a turbulent flow was much higher than aerodynamic heating in a laminar flow. And it is possible, seen data, where you can have a local increase in the heat transfer just due to transition from laminar turbulent flow, where the peak heat transfer is actually higher than the stagnation point heating. So the stagnation point is not necessarily the point of maximum heating. Another example would be in a shock wave boundary layer interaction. Whenever you have a shock wave impinging on a surface and interacting with a boundary layer, at hypersonic speeds, you get local peaks of heat transfer where that shock wave impinges on the body. And it is possible to get exceptionally high heat transfer rates in that impingement region that can be higher than the stagnation point. But for most situations, I mean, the stagnation point heating is really where most of the heating is at, and that's where you pay a lot of attention. That's why you pay a lot of attention to the nose region. Now, let's go on to continuing our discussion of viscous flows. This is about all that I'm going to say about boundary layer effects and just these brief comments on aerodynamic heating that have to do with solutions of the boundary layer equations and hypersonic speeds, because I want to take some time now to go into a slightly different viscous problem, and it is this. On our roadmap, I'm sorry, I faked out our technical director here. On our roadmap, I want to come down here under viscous flows. I want to talk about viscous interactions for a few minutes. Viscous interactions. What are we talking about there? And so for the next few minutes, we're going to be launching into, in your notes, again, for those of you who have the book, Chapter 7, Hypersonic Viscous Interactions. Let me remind you again something I mentioned a few minutes ago. On page 303, there is a derivation. I'm going to show you the result that says that for a laminar boundary layer, the thickness of a laminar boundary layer in hypersonic flow is proportional to the square of the Mach number and inversely is the square root of the Reynolds number. I want to remind you again that this is a characteristic result of compressible flow boundary layer theory. The boundary layer thickness varies as the square of the Mach number. So as you increase the Mach number, everything else being equal, the boundary layers can become very thick. Now when the boundary layers become very thick, we introduced this idea earlier this morning. When the boundary layers become very thick, some strange things happen to the flow. Not strange, but some important things happen to the flow. First of all, let's visualize flow over a flat plate, and let's visualize inviscid flow over a flat plate. Say we have flow coming in here, inviscid flow, no friction effects. It goes zipping past the flat plate as if the flat plate weren't even there, and indeed it's not even there as far as the inviscid flow is concerned. And we have nice uniform flow, and if we plot the pressure on the surface of the flat plate, we would have a pressure distribution that gives us constant pressure as a function of distance along the flat plate. So that's the inviscid flow picture. Now, let's go to the viscous flow picture. The effect of friction causes a boundary layer to be built up along the surface of the plate. We've just finished saying that this boundary layer can be thick for a hypersonic flow, high Mach number. What this will do now is essentially make the flat plate look like an effective body with some effective thickness. A shock wave will be triggered at the leading edge of the plate. Flow will be deflected and going around that shock wave. And if you would measure or calculate the pressure along the surface of this plate, we'd get a pressure that would look like this. The pressure would be at a higher value above the inviscid flow value. And in fact, as you go nearer and nearer the leading edge, the pressure becomes higher and higher. This is called the induced pressure, and this is a picture of what we call the viscous interaction effect. Why is it a viscous interaction? What do we really mean by the word viscous interaction? Let's go to another figure. This is now on page 306, figure 7.2. Let's look at more in detail physically of what's happening. Near the leading edge of this plate is a region where not only do we have viscous interaction occurring, but it's something that's called strong interaction. Now what do we mean by strong interaction? It means this, that the boundary layer, the rate of growth of the boundary layer thickness, the d del star dx, is so large that it affects the outer inviscid flow. It makes a strong change, it creates a strong change on the outer inviscid flow, which in turn is fed back to affecting the rate of growth of the boundary layer. So by definition, a strong viscous interaction is one where the boundary layer is affected by the outer inviscid flow, and in turn the outer inviscid flow affects the boundary layer. Now if you go far enough downstream, you reach a region that's called the weak interaction region, where the boundary layer rate of growth now is a little more moderate. The outer inviscid flow is only weakly affected by the boundary layer, and therefore we don't bother to feed it back into the rate of growth of the boundary layer itself. In this region, this is called the weak interaction region. Now, the boundary layer properties, the pressure distribution along the surface, and other properties of this viscous interaction from a theoretical study of this type of flow, can be shown that the governing parameter for this viscous interaction is something called chi bar. This is important to remember. Chi bar, by definition, is m infinity cubed over the square root of the Reynolds number times the square root of c, where c is called the rho mu ratio, is density times the viscosity coefficient of the wall divided by the density times the viscosity coefficient at the outer edge of the boundary layer. Chi bar, this is a correlating parameter for viscous interactions. Why is it a correlating parameter? We'll see. The results of boundary layer theory coupled with the outer inviscid flow shows on page 312, I'm going to show you an equation. For the strong interaction region, the pressure distribution correlates just with chi bar. There's nothing else in there. There's no Mach number, Reynolds number, distance, anything. It falls out that the pressure is just a function of this chi bar. Let me remind you again what chi bar is. M infinity cubed over the square root of the local Reynolds number times the square root of c, and this is c. And that is such an important parameter that the pressure depends just on it. Pressure is a function of distance. The distance x is buried in the chi bar. It's buried in the chi bar through the Reynolds number, which has an x distance in it. Okay, that's for the strong interaction. For an insulated flat plate, we can go for the weak interaction at the top of page 313. Same type of correlation. We'll wait for this to come up. Our pressure is still a function of chi bar. If we have a cold wall case, the pressure is still a function of chi bar for strong interaction. I'm going to correct a typo here. For those of you who have the notes, page 704, equation 741, page 313. This number should be 0.15. But that's, for our purposes here, that's not important. What's important is that, again, the pressure just depends on this chi bar. For the weak interaction regime, same thing. If you don't believe the equations, here's some experimental data. Experimental data measured on flat plates, pressure distributions, and let's see, we're supposed to stop at 2:30, right? Oh, phone call coming in. Time out for a phone call. This is exciting. Let's see what happens.
Dr. Anderson.
Yes.
A moment ago you said that the high stagnation point heat transfer and its effect, or its inverse relationship to the nose radius, is the reason for the use of blunt bodies in hypersonic flow.
Yes.
Does that imply that for an adiabatic surface you would not use blunt bodies?
Oh, good question. That's not true, because what happens when you have an adiabatic surface? By definition, an adiabatic surface means that your wall temperature, okay, let's take 60 seconds. Let's go through a 60-second scenario. Here's a body. This body is a cold body. It's at room temperature. Let's now take it up to 200,000 feet and start flying it at Mach 25. And we have 1 minute to go. We start flying this at Mach 25. At 0 time, the surface temperature of the body is room temperature. But now, there's lots of heat transfer to that body. And so the surface temperature is going to start heating up. Surface temperature is going to get hotter and hotter. As the surface temperature gets hotter and hotter, the amount of heat transfer begins to reduce, because in these equations, let's see if I can quickly find one for you. Let's go back and look at this. In the equations, there's not only the nose radius, there's the velocity gradient that appears there, but also, I'm going to come up with it here in a minute, but also there is, for example, an enthalpy difference, adiabatic wall enthalpy minus the wall enthalpy. And so back to our scenario now. As the wall temperature gets hotter and hotter, this enthalpy difference gets smaller and smaller. And so the heat transfer begins to get smaller and smaller. But the important point is the temperature is getting hotter and hotter. And sooner or later, you're going to reach its wall temperature here where it's hot enough that there isn't any more heat transfer to the surface. Now, the key is hot enough. For the blunt nose body, let's put it this way. If you have a certain amount of stagnation point heating coming into the nose, The larger that nose radius is going to be, the lower the heat transfer, and the lower will be the adiabatic wall temperature, everything else being equal. And so in answer to your question, what you're really talking about there is, sure, when you have an adiabatic wall temperature, by definition you have zero heat transfer. But your large nose radius is helping you to have an adiabatic wall temperature which is going to be lower than it ordinarily would be than if you had a smaller nose radius. Does that make any sense to you out there? Or is he still on? Are you still on the phone
Yeah.
there? Okay.
Thank you.
It's a very good question to ask, and I'm glad you asked it. And besides, I want to use this to serve other people on the outside to feel free to call in and ask questions like this so we can talk about things. And with this, I think we're off the air because we're over 2:30. So we're due for, according to my schedule here, a half-hour break. Why do we have a half-hour break? That's to give those people on the West Coast a chance to have lunch. So we'll see everybody back here at 3 o'clock.